couple of displacement reactions occur between two different ionic compounds. And these two ionic compounds in solution will react with one another to form a different set of ionic compounds. So here what I've written is silver nitrate with AQ as it states, so that's aqueous, it's dissolved in water. And I've written sodium chloride with AQ in the aqueous state, it's dissolved in water. And when I mix these two solutions, what I'm likely going to see is the formation of a precipitate. And the formation of a precipitate is evidence that there's an actual chemical reaction that occurred, because a precipitate is a substance that comes out of solution. It comes out of the dissolved state. It crystallizes. And this is because it has a low solubility in water. So, question is, does this particular reaction form a precipitate? Well, to figure that out, I need to think about what ions are present in the solution when I mix these two solutions together. So, what I'm going to do is actually write the reactants differently just below. And I'm going to write it as part of what I call a total ionic equation. I say I call, that's very incorrect because I didn't come up with this name. People use this all over the place in chemistry textbooks, so I did not coin this phrase, total ionic equation. So what I'm going to do here is I'm just going to write silver nitrate as its dissociated ions. So Arrhenius said that ionic compounds will dissociate to form ions in solution. So silver nitrate in solution is actually just a collection of silver ions and nitrate ions. Sodium chloride is just a mixture of sodium ions and chloride ions. So when we mix these two substances together, we get a mixture of ions. And the question about whether they form a precipitate or not really has to do with the question of, okay, is there some combination of ions in here that when they're mixed together or in each other's presence, they form something that is insoluble in water? So what we usually do here is we consult a solubility table. In a solubility table is a record of which combinations of ions mix to give us a compound that has a high solubility in water or a low solubility in water. So on this row here, this is the very soluble row. And what we usually do is we look for an anion and see which pairings produce something that's very soluble or which pairing produces something that's slightly soluble. So I've got these 4 ions in solution. My anions are nitrate and chloride, and my cations are silver ions and sodium ions. So let's start off with what's one possible new thing that we can make here? Well, I could make sodium nitrate. So the sodium and the nitrate, they could end up with each other here. So let's see if they're going to be soluble or insoluble in water. So first I find nitrate. Nitrate's over here, and it says nitrate is very soluble with everything. So you see nitrate or even, chlorate or perchlorate here, they're soluble with everything. So sodium compared with nitrate, okay, that goes in the all cell right here. So that means sodium nitrate is going to be soluble in water. So one of my products here is going to be sodium nitrate. It's soluble in water. Great. So I put an AQ behind it. The other possible combination I can get, a new combination I can get out of this, is silver ions mixed with chloride ions. So let's see what their solubility is. So chloride ions paired with silver ions give us a compound that is just slightly soluble, which means it's, we could call it insoluble here. It is going to precipitate. It's going to come out of solution. It's going to fall out of solution. So that means when I write out silver chloride, I'm going to write an S to mean it's in the solid state. And in the context of this particular reaction, that means it's a precipitate. And precipitates kind of look wispy, cloud-like. They look different from the solution that they're in. And I'll just draw one out quickly. They'll probably fall to the bottom, and you've got this like kind of clumpy thing at the bottom. I'm not sure what color I'm going to do it in. Just to be different, why not? Let's just do it in orange. This is not the actual color of silver chloride, but this is just to show you that when you get a precipitate, it eventually, like if you spin it, put it in a centrifuge, or just let it sit for a while, it'll kind of fall to the bottom. Sometimes it'll stay on top. When we're doing this kind of stuff in a high school lab for like, I don't know, a 20-30 minute experiment, usually they just kind of look wispy and cloud-like, and they look different from the rest of the solvent, okay, the rest of the solution. So in this case, silver chloride would be a precipitate, and there you have it. So what I want to do now is return to our total ionic equation. So here I wrote out my reactants as dissociated ions. Now what I'm going to do is I'm going to write out the products as dissociated ions where appropriate. So the only thing that I can write as dissociated ions are the things that are in the aqueous state, because that means they're dissolved in water. So that means I can take sodium nitrate and I can write it as sodium ions and nitrate ions. Now, silver chloride is in the solid state. That means it's not dissolved in water, and that means it is not a collection of its ions. So that means I have to keep silver chloride written as being in the solid state, and it's not written as its ions, its dissociated ions. All right, so here I've got a total ionic equation. It's showing everything that's in the aqueous state as a collection of its cations and anions dissolved in water, and I've got the precipitate in the solid state. But what I'm going to do now is I'm going to get rid of some of the fluff, some of the stuff that doesn't change. And in that process, we make something called the net ionic equation. So once you write a total ionic equation, to turn that into a net ionic equation, you need to get rid of the stuff that doesn't change. And to figure out the stuff that doesn't change, we need to look at the entities that do not change state. Basically, we're looking for things that don't change at all. They don't change their state, they don't change their charge. So what are those things? So looking through my total ionic equation, you'll notice that nitrate ions remain as nitrate ions. They don't do anything. They don't go through any sort of change. Is there anything else that doesn't change? Well, you'll notice that sodium ions also do not change. Sodium ions are in the aqueous state. On the reactant side, they're in the product side, also in the aqueous state. Same thing with nitrate. So these entities that don't change, we call these, let's include sodium in there, we call these spectator ions. Call them spectator ions because they're really just watching the reaction. They're not participating in the reaction. They're just spectators. They're watching it, but they do not participate in it. So they're not really all that essential for the reaction to take place. Sometimes you can view them as expendable. You could probably sub out sodium here for potassium ions, and you'd get the same result. The actual reaction that is occurring is what we're going to write out in our net ionic equation. And what we write in the net ionic equation is silver ions plus chloride ions I'm going to use a single arrow here, showing us that silver ions and chloride ions come together to form solid silver chloride. And this is what the net ionic equation is. In the net ionic equation, I am showing the pure chemical reaction. I'm showing the entities that go through a chemical change. And the things that I know go through a chemical change will go through a change of state. Okay, this is showing, and this is actually showing that silver ions plus chloride ions are coming together to form a insoluble compound. So they're forming a bond together, an ionic bond. They're forming a crystal lattice. The silver chloride solid here will form that compound, and they're coming out of solution. By removing the spectator ions, we get to the guts of the reaction. So when I look back at this double displacement reaction, what is really going on? Well, the thing that's really occurring, the precipitation of silver chloride, is this. Okay? The thing that's really going on in the double displacement reaction is this here. Everything else is fluff. So in the total ionic equation, we remove the spectator ions and we get down to the guts of the reaction. Okay, and that's the purpose of writing a net ionic equation. We also use precipitation reactions like this. We use different ionic compounds to precipitate other ions out of solution, and that's part of doing something called qualitative analysis, which we're going to look at more closely in the future. All right, that's it for this video.